$47,000. That's the amount of money that one single AI agent burned for a client of ours. And the crazy part, it wasn't because the team crashed or because it threw errors. Actually, every single API call was coming back successful. The agent was working perfectly fine, but had no idea how to stop. So what happened was, this thing had been sitting there and calling the same 3 endpoints for 11 days straight, just rephrasing the same query over and over and getting the same answer back every time. I'm burning tokens while doing it. 11 days, and nobody had even looked at the dashboard until the bill came in with $47,000 gone. And the thing is that the agent had absolutely no guardrails. So what I want to do today is to walk you through 5 systems that will have got this in minutes instead of 11 days, and that are the exact same thing that we built for this client. So here's what's going on right now. Everybody and their mother is building agents, right? LangGraph, CrewAI, OpenClaw, custom setups even. Like, agents are literally everywhere and they are getting really capable. But here's the problem. Gartner, which is one of the biggest tech research firms out there, they just came out and said that more than 40% of agentic AI projects are going to get scrapped by 2027. And that's not because the agents aren't smart enough, because they are capable, but because they're just too expensive to run reliably. And it's always the same story, right? There is no safety net, so your agent hits some ambiguous state, it starts retrying, and then your build just goes completely parabolic overnight. Let me actually show you how fast this can spiral, because I think the math is what really makes it click. So GPT-5 input right now costs about $250 per million tokens. And if you got an agent that's averaging around 4,000 tokens per step and it's running a step every 3 seconds, well, that works to about 1,200 steps per hour, which means you're burning through almost 5 million tokens per hour. That's $12 an hour, $288 a day. And if that thing just keeps going for a month, you are at $8,600. And keep in mind, that's just one agent. The moment you start stacking multi-agent systems with tool access, that's how you end up with the $40,000 territory real quick. So what I've got for you are 5 guardrails. And the nice thing is that each one of these is completely independent. You can pick up any of them and implement it today. But when you put them all together, they form a full safety stack. So let me walk you through each one. Most basic guardrail that you can build is an iteration cap. And most people already do something like this, but the way they do it is wrong. Then you set like max turns equals 10 or 50 and they call it a day, like it's ready. But the issue with that is a simple lookup task and a complex research task are both getting the exact same budget. So the simple one ends up wasting a bunch of steps before it finally hits the cap, and the complex one gets cut off right in the middle of doing actual work. So the way you actually fix this is with task type budget. Basically, before your agent even starts doing anything, you classify what kind of task it is, and then you assign it an iteration budget based on that. So for instance, a lookup gets 5 steps, analysis gets 15, research gets 30, because if lookup is taking 30 iterations to finish, there is definitely a loop and there is something wrong going on in there. Here's the thing though, iteration caps by themselves, they're not going to save you, because really nasty loops, they don't hit the cap at all. They will run 20 iterations that all look completely different on the surface, but they are actually accomplishing not. And that's exactly where guardrail number 2 comes in. So this is the one that almost nobody implements, and it's probably the most important in this whole list. The basic idea is that you hash your agent recent actions and then you check whether it's just doing the same thing over and over again with tiny little variations. The way it works is that you keep a sliding window of the last 5 actions, and for each action you normalize. So you lowercase everything, store the keys, strip out the white space, and then you hash it. And if 3 out of those 5 actions end up with the same hash, that means you have got 60% duplicate ratio. And at that point, your agent is definitely looping. And the reason that the normalization step matters so much is that a looping agent doesn't actually repeat itself word by word. Like, it will call the same tool, but with a slightly different formatting, or it will rephrase the same query a little bit each time. So by normalizing everything before you hash it, you're able to catch up all those near duplicates that will otherwise just slip through. And you can actually see this playing out right here. The agent starts by searching for quarterly revenue, and then it tries Q4 revenue numbers, and then it tries something like revenue for 4 quarters. But every single one of those normalizes down to the same hash. So by step 5, you are already at 80% duplicate ratio. So we detected the loop and we stopped the agent. And now if you want to complicate the things and get more sophisticated with this, you could use embedding similarity instead of just exact hash. It's the same basic idea. You embed each action and then compare the cosine similarity against residue. And that lets you catch semantic loops, not just the string identical ones, which is good to a certain point. But to be honest, the such approach is going to catch like 90% of the leaves you will actually see in the real world. So I will start there. All right, so this next one is pretty straightforward, but it's absolutely critical. The idea is that you track your token usage in real time and you are forced to separate results. Okay, so let's see how this actually works. So the soft limit doesn't actually kill the agent. What it does is force a model downgrade. So let's say if your agent was running on GPT-5, well, now it drops down to GPT-5 mini. The task, of course, keeps going, but you are paying a 60th of what you were paying per token. And then your hard limit, that's your emergency brake. That's a full stop. Just return whatever results you have collected so far and then shut it down. And you can see the three zones laid out right here. So when you're under $2, everything is normal, full model, no intervention, everything works as usual. But once you cross the $2 mark, the soft limit kicks in and then you get the model downgrade. And then if somehow you make it till the way to $5, that's the hard limit and that's where it just stops completely. Now, as for what dollar amounts you should actually use, that's going to depend entirely on your use case. For us, a typical agent task usually costs somewhere between 50 cents and $2. So if we see something approaching 5, we know something's going wrong. You just need to figure out what normal looks like for you or for your system and then set your limits based on that, which actually is exactly what the guardrail number 4 helps you do. So the first 3 guardrails that I show you, those are all about protecting the single run. This one is different because it's about protecting the whole system over time. And I actually have a story for this one. So we have this monitoring system running across a bunch of our AI pipelines and everything looked totally fine. There were no errors. The responses were coming back. Users were happy. This was used for our clients. But what was happening underneath was that the cost per run was slowly creeping up. Not dramatically or anything, just a little bit each week. And what we actually figured out was that a dependency update had quietly changed the default token limit of one of our models. So every single response was coming back with about 30% more tokens than it used to. And when you are running thousands of tasks a day, that turns into an extra $8,000 a month, but we were just bleeding out. And nobody caught it because there was nothing in the logs, like literally 0 errors. Everything looked perfectly healthy. So the fix for this is actually really simple. You keep a rolling window on your last 100 runs and you calculate the mean on the standard deviation. Then if a new run comes in and its cost is more than 3 standard deviations above that mean, that's your alert right there. And look, this is not some fancy statistical technique or anything. It's the exact same pattern that you will use for any infrastructure metric, CPU usage, memory request latency, just that you're applying it to your token spec. And the alert that caught our $8,000 bug, it was this exact pattern. The run cost crossed the threshold on a Tuesday morning and we were able to trace it back to that dependency update in about an hour. And without this thing in place, we would just have to keep burning another 8 grand for the next month and the next month after that. All right, the last guardrail, and this one really changed the way you think about agent failure because most guardrail, when they trigger, they just stop. The agent hits some limit, the whole thing crashes and the user gets absolutely nothing, or even worse, they just get some generic error message that tells them nothing new. Circuit breaks works a little bit different. So when your agent trips a guardrail, instead of just dying, it actually packages up everything it has so far and returns that along with an explanation of why it stopped. And just look at the difference here. On the left side, you have this generic message of error, agent terminated, no results returned. And this is completely useless, right? From a user perspective and from a developer perspective, this says nothing about what happened. But on the right, we have a very well-structured error message that says partial result, 8 of 12 tasks completed, stop it because loop detected at step 9. Here's what I found so far. Now, this is absolutely useful and the user can work with that. And I think this is really more of a design philosophy than just a code pattern. Your agent should literally never just vanish on the user. If it hit the iteration cap and tells something like, hey, I got through 8 out of the 12 sub-tasks before I hit my limit. Here's everything I found. And let's say that if it hit the cost budget, something like I had to switch to a faster model at step 6. So the rest of the analysis is a little bit less detailed, but here's what I've got. And at the end of the day, your users don't care that there are guardrails running behind the scenes. What they care about is getting something useful back. The circuit breaker is what makes all of these guardrails invisible to the end user because the experience stays smooth even when something everything goes wrong. Okay, so let me put all this together for you. Here's what the complete Guardrail stacks looks like. Every single step that your agent takes passes through all 5 of these checks. The iteration guard is counting steps. The loop detector is hashing actions. The cost budget is tracking tokens. The anomaly detector is comparing everything against your baseline. And then at the end, we have the circuit breaker that is just sitting there, making sure that whenever any of those guardrails trips, the user will still get something useful back. So let's go back to that $47,000 agent for a second. If we had just a slap on the cost budget alone, we'd say a soft limit at $50 and a hard limit of 100 if you want to be generous with the agent. That agent will have a stop in under 4 hours instead of running for 11 days, which it is already a lot. So we pass from days to just 4 hours. And if we will have the loop detector, it will have been caught in under 10 minutes. And without 5 of these working together, 100% we will caught this in under 2 minutes. And here's the thing that really gets me about this whole OpenClaw incident. This full agent that they were running, by the way, it was OpenClaw. That agent was running for 11 days. All right, so 11 days of API calls, and every single one of them came back successful. There was no errors anywhere in the system. And that's only the scariest part, that everything looked completely healthy because we built all these dashboards to catch errors and failures, right? But the really expensive disasters like $47,000 on a loop, they just don't look like failures. They look like success, just way too much of it. And the guardrails I show you, we are talking about maybe 150 lines of Python total. That's it. And those 150 lines are the difference between an agent you can confidently leave running overnight and one that might eat your entire quarterly budget while you're asleep. So if you're running agents in production right now, my advice will be definitely to start the cost budget and the loop detector. Just those 2 alone are going to catch the majority of the baddie scenarios you will run into. And then as your system matures and grows, you can just layer the other 3 on top of it. And if you want to see the cost optimization side of this, like how to actually bring down what your agent spends on each individual call, I made a whole video on that. So I will link it here. And if I cannot do it because of YouTube, you can just go to my channel and it's going to be the previous video to this one. All right, so more stuff like this one is on the way. And if this is your world, go ahead and subscribe, and I will see you in the next one.